Okay, welcome again to our seminar, our weekly seminar. This week we have a PhD speaking on SongSu Son. He'll talk about thin, quiet, long-lasting, high-friction surface layers for Illinois, especially. Just a little bit of background on SongSu. He's working for Professor El-Kadi, and he's been here for several years. Yeah, and I don't know if I'd say several years more, but at least he'll be done sooner than later. He's obtained 2 degrees in Korea, one from Chang'an for his bachelor's, and Seoul National University for his master's degree. I didn't know that he worked in Morocco also, so he had some experience there and learned French. So I learned a lot already this morning about other work he's done. And so today we're looking forward to hearing about what he's been doing. Before SongSu starts, next week, October 25th, Maziar, is he hiding in here? No. He's presenting on his imaging work. 2 weeks from now is our staff person, ICT staff editor, Peggy Curran, so please attend that. Especially because she's going to go over some basics of editing, scientific writing, which you may think is not very important, but as a faculty member, I can attest to 100% that all students can improve their writing, and if it does improve your writing, it does make our life a little bit easier reviewing your reports and get them back to you faster, because I know everybody wants things to move fast. So plan on attending that. And then 3 weeks from now, Deb is going to speak on some settlement measurements on bridge approaches for railroads. Okay, SongSu. Thank you.
Yeah, I'm a PhD student working with Professor El-Kadi. I'm currently working on one of IDOT project, which is the development of a thin, quite long-lasting, high-friction surface layer for economical use in Illinois. Actually, I cannot remember this title of my project. I'm usually called the thin, quiet pavement or the thin, durable pavement, but this is the title of my project. Actually, for last several years or this decade, the oil prices kind of keep increasing, or at least is unstable actually. So IDOT developed the cost-effective asphalt mixture for wearing surface. So, but even though we developed the kinds of cost-effective asphalt mixture, this mixture should promise the similar performance, or at least, or the better performance than the current mixture they used in the wearing surface. So it should be durable and thin and low noise and high friction. And the most important thing is should be cost effective. There is a 2 ways to, reduce the cost. The first one is to reduce the thickness. So in that case, we can save the money to reduce the materials amount. Another one is to replace the materials with a less expensive aggregate or the asphalt binder. So actually, in this project, we try to develop the 4 new mixture using these 2 approaches. So to compare with the new mixture, we selected 2 contour mixture that is currently used in Illinois as the wearing surface mixture. The one is 9.5 dense grade HMA. Another one is 12.5 SMA mixture. In the lab, for the cost-effective asphalt materials, we developed the 4 new mixture. The first one is quartzite mix, and then sprinkle mix, and slag fiber mix, and 4.75 SMA. So I'm gonna talk more detail about it later. So now we have 6 mixture, including the 2 control mixture and 4 new mixture. So for this 6 mixture, we conduct the laboratory test, and also we conduct 4 field testing. For cost, to see the engineering benefit so we did the engineering benefit analysis, or the cost analysis of this mixture. Laboratory experimental program. We try to use the locally available aggregate as much as possible, because it saves the money, because we can reduce the transportation fee or the cost, and also if you use the most popular aggregate in Illinois, it is better than to import the aggregate from other states. So in Illinois, actually, the limestone and dolomite and the natural sand are most popular aggregate here. But the limestone is not allowed for asphalt surface layer because it's not strong enough to use in the asphalt surface layer. And also natural sand, we try to minimize to use the natural sand because of the round shape. If you use too much natural sand, you might have the rotting issue. But to save the money actually for the material cost, we try to use this dolomite and natural sand as much as possible, but try to minimize the use of the natural sand too. And also some of the mixture use the steel slag. This is the byproduct of the steel. So it's cheap, relatively cheap, but this steel slag is very strong and then has a rough surface. And also we use the quartzite. This quartzite, we imported from the other states. So the asphalt binder used in this project is PG70-22 and PG76-22 SBS modified binder. To minimize the variation from the other source, even though we use the dolomite, if we sample this same dolomite from the 2 different sources, we might have some variation because of the source. So we sampled all the aggregate used in control mix and then new mixture from the one plant actually. So I think we minimized the variation of the aggregate from the different source. Here is the 4 new mixture. The first one is a fiber slag mix. We use the steel slag for this mixture to reduce the material cost. But this, because of using the steel slag, we expect high friction and good resistance to the stripping and rotting. And also, by adding the fiber in this mixture, we were expecting to have the higher tensile strength. Because if we put the fiber, actually, this fiber holds the materials. So when we have the reflective cracking or this kind of the cracking, the fiber holds the materials. So even though we reduce the thickness, actually the tensile strength at the bottom of the asphalt layer is always the issue. So when we use if we use the fiber, we can reduce the thickness. So that's our idea at the beginning. So second one is 4.75 SMA. I think for last couple of years, so NCAT or some other states, they developed the 4.75 dense gradient mix. So if we have the smaller nominal maximum aggregate size, we can reduce the thickness. Usually for dense grade mixture, the minimum required thickness, layer thickness is 3 times of the nominal maximum aggregate size, and 4 times for SMA mixture. So if we have the small, the nominal maximum aggregate size, we can reduce thickness. So this is the concept of the 4.75 SMA. But as I mentioned before, some states developed the 4.75 dense gradient mix. But the problem of this 4.7 dense gradient mix is the surface is too smooth. So the friction is always an issue on those mixture. So we select the 4.75 nominal maximum aggregate size, but we designed this to be the SMA gradation, to have the relatively rough, the surface. The third one, quartzite mix. So we just put the quartzite aggregate inside. The quartzite is very durable aggregate, so we were expecting to be the very durable in this mixture. The fourth one, sprinkler treatment. This is actually used a long time ago in Illinois and Georgia, actually. But recently, people didn't use this the mixture or the treatment that much. The main idea of this mixture is we just use the regular or the cheap, the base mixture, asphalt mixture. But after we place these materials in the field, before we compact, we spread the very coarse aggregate on top, and then compact. So it's like a chocolate chip cookie. We just spread the very strong, the coarse aggregate on top, and then compact. So this will increase the friction on the surface. So, but by using the less expensive base materials, we can save the money, but we can increase some friction performance. This mixture. So here is the mix design summary for 6 mixture. We have 12.5 SMA mixture and 4 9.5 dense gradient mix, but the control mix has the coarse dense grade, but our new 3 mixture has the fine dense grade mixes. We use the Bailey method to design this aggregate, the gradation. So the big difference of the coarse dense grade and then fine dense grade is kind of aggregate the structure. So for fine dense grade, I think I will show you the one of. Yeah, here is fine dense grade. Let me see. Okay. You can see the coarse aggregate is floating in the mixture. But here is the coarse dense gradient mixture. You can see the contact of the coarse aggregate. But this is the SMA mixture. So the benefit of the fine dense gradient mixture is we can get as people say, the compactability. If you use the fine dense gradient mixer at the thinner the layer, we can have the target density even at the thinner layer. But 9.5, the control mixture, when I talk with the plant people, they said they cannot compact actually this mixture less than 1¼ inch thickness. So, but we had a good density, even 1 inch or less than 1 inch by using this fine dense gradient mix. So to have the compactability and thinner layer, we designed the aggregate gradation to be the fine dense gradient by using Bailey method. We used the P70-22 for all of the mixture except 12.5 SMA. We cannot control this too because this is commonly used in the Illinois. So we just sample these 2 materials from the plant. So what else? For 4.75, usually for SMA mixture, we should use more asphalt binder to hold this gap grade the aggregate. So 4.75 SMA had the highest asphalt contents here. Yeah. Specimen preparation. We had three groups of the specimen or the specimen preparation. The first one is we batch the aggregate and then mix in the lab and then compact in the lab using the gyratory compactor. Second one is we sample the materials, loose material from the plant, and then compact in the lab. The third one is plant mixed and the field compact. This is the field mixed and then compacted by the roller in the field. We took all three samples and then did these 5 performance tests in the lab. So here is the matrix for lab mixed and lab compacted mix, and then plant mixed and lab compacted. We did the 5 performance tests, and also we took the course right after construction and then 4 months after construction. But because of the core size, we only conduct the rotting test and fracture test in the lab. And also we did the full field testing after the construction, right after construction, and also every 4 months after construction, up to 1 year. So that's why we have the 0 months, 4 months, 8 months, and 12 months. So after 1 year, we do this same test every year. So the next field testing for 24 months will be the next month, actually. Yeah. So first, the lab test is simple performance test. So according to the Ashoto spec, first we make the gyratory sample and then take a course and then did the complex modulus test at 5 different temperatures under 6 different frequencies. If you see here air void for dense grade mix and SMA mixture, actually we try to have the same air void, but from kinds of the discussion in the TRP meeting, actually for dense grade mixture we are targeting have the 93% of the density in the field, but for SMA mixture we are targeting 94% of the density. So if we compact this SMA mixture to have the 7% air void, it's not correct in the field. So that's why we decided to have the 6% air void of all of the SMA mixture. So as you can see here, this is the master curve of the 6 mixture. It's a plant mix and lab compacted specimen. From the complex modulus, we can generally pick up the 2 points here and here. This point is more related to the kinds of fracture performance. It's low temperature and high frequency area. So here it's high temperature and low frequency. It's more related to the rotting. So as you can see, we only use the PG76 76-22 for the control SMA. So for other 5 mixture, we use the PG70-22. So you can see the modulus is almost identical in this area, but it's kind of high temperature area. You can see the higher modulus in the control SMA mixture. The second one is the moisture susceptibility test. We did the TSR test according to the Illinois modified specification. For wet condition, after we make the gyratory samples, we saturate them to be to have the 72 70 to 80% of the saturation level, and then put a condition them at 60 degrees C for 24 hours. After then, we put these samples in the 25 degrees C water bath for 2 hours, and then we conduct the IDT test. For dry condition, we just the condition at the 25 degrees C for 2 hours. Also, we have the lab mixed and the plant mixed, but both are compacted in the lab. As I mentioned before, we didn't make control mix in the lab. We just sampled from the plant and then compacted in the lab. So we have only we have the control mix only this part. So, but this part we can, compare the performance between the new mixture. Illinois TSR threshold is we should have have 85% of the TSR value and then 60 psi minimum strength. So all of our mixture meet both the threshold. And to compare with the control mixture, new mixture, we can see this the columns actually. So new mixture will pass the TSR. Yeah, new mixture are observed to have the higher tensile strength than the control mixture. I'm sorry. Yeah. So, but TSR value from the plant mixed. So actually, after we sample the materials from the plant, we actually to make a gyratory sample, we reheat the materials and then compare. So in that case, the property of these materials or something happen in the mixture. So we, even though you can see the 82 or the 83.9 didn't satisfy the threshold, but this is the reheated materials. So we didn't kinds of take care of this TSR value from the reheated materials. But to compare the IDT strengths, we use this number to compare our new mixture to the control mixture. The third or fourth test is durability test. According to Texas DOT, the specification, first we made the gyratory samples to have the 115 height and design air void. So we measured the weight of this gyratory specimen. And then we put this gyratory specimen in the LA abrasion machine without steel ball. And then we rotate 300 times, then take it out, and then measure the weight of the specimen. So, and then calculate the loss of the materials. So if we have the higher number here, that means it's less durable. So as you can see, new mixture are expected to be more durable than control mixture. And also the highest loss was observed with the control SMA because of its larger nominal maximum egg size. As you can see, this is 12.5 mixture. The 4 mixture in the middle is 9.5. The last one is 4.75 SMA. But again, this 4.75 SMA had a higher asphalt content. So this provides the less or the least the loss of the materials after 300 times of rotation. Next is the rotting test. Using the Hamburg wheel tracking tester, we made a specimen and then did the test at the 50 degrees C of the water bath, and then applied 20,000 passes, and then measured get the maximum displacement of the surface. The lab prepared the specimen. The 4.75 SMA provide higher rot depth because of 7.3% of the asphalt contents compared to the others with around 6% asphalt contents. But for the for the plant mixed and lab compacted mix, we have almost identical rot depth after 20,000 passes of the steel wheel for all of the mixture. Yeah. And also we did the rotting test using the field cores. Here's the F mix, core size mix, and left L means that this is one lane. We took the 6 cores from one lane. This is the left wheel path in the center of the lane, and the right wheel path. So left to center and the right wheel path. As you can see, actually the rotting performance is very sensitive to air void. So we measure the air void of these cores before we do the rotting test. As you can see, right wheel always provide the higher air void because when we place the materials in the field and then compact, the right side is unconfined. So when you apply the same number of the passes, actually right wheel or the right side of the lane always had the higher air void. So, and also we took the cores after 4 months after construction. So after 4 months, the air void significantly dropped, and then coarse dense grade show the higher air void drop than fine dense grade and SMA mixture. And then wheel path, air void in wheel path, drop the more than center of the lane. Yeah, this is already. Yeah, because of we have the higher air void on the right wheel path, the rot depth was higher than the center and left wheel path. The other one is the fracture test. We use the semicircular bending test. After we make a gyratory sample, we sliced it and then cut into the half and then made a notch and then measure the ligament area to calculate the fracture energy. We did this test at 2 temperatures, which are the -12 and -24. Significantly, actually, for control SMA mixture provide the highest the fracture energy, but for sprinkle mix was the lowest because we just used the regular or the cheap materials for the sprinkle mix, but we spread the sprinkle chip like choco chip cookie. But the 4.75 SMA mixture showed the higher the fracture resistance among the new mixture due to the higher asphalt contents. As I mentioned before, actually we were expecting this slag fiber mixture to have the higher fracture energy because the fiber hold the materials when we do the fracture test actually. But still, it looks very, it's relatively lower than 4.75 SMA. But we noticed this fiber slag mixture has a very high COV of the fracture test result. So we took a look at the surface, at the face of the fractured face. But some specimen showed the fiber along the crack propagation area, but some is not. So fracture energy is depending this mixture is depending on whether fiber is located in the crack, the propagation area or not. So blue one is without the fiber in this fractured face, But this red one had fiber in those area, those face. So you can see the long tail of the fracture curve actually. So that means the fiber hold the materials after the crack initiate. So in this case, a fiber at the fracture area increased the fracture energy by the 57%. But we add the fiber in this mixture around 0.05% by weight of asphalt mixture. This is the
weight or volume? Weight or volume?
weight. So to make the one, that's why in the plant, when they produce the 1 ton of the material, they put the 1 pack of the fiber. 1 pack has 1 pound of the fiber. So it's 0.05% of the fiber. This is recommended by kinds of company actually. So we use the same percent or same amount of the fiber in the mixture. Fracture tests. We did the core. We did the fracture test for field cores, and also after 4 months, actually fracture energy was increased because of the density also increased after 4 months, and also there might be the aging effect during the 4 months. Yeah, I think I need to speed up a little bit more. We placed this 6 mixture in the field site, which is close to Schaumburg in Chicago. First, we put the F mix in 4 sections with 2 different thicknesses to see the thickness effect on the performance. But we also put the 2 sections here with the same thickness of the same materials because to see the traffic effect. Even though we are assuming the same traffic, so there might be some difference between the direction. So that's why we put the same materials with the same thickness here at 2 different directions. For our new mixture, we placed these materials at 2 different thickness. One is 1 inch, another one is 1¼ inch. But we tried to place the F mix at the 1¼ inch too, but it didn't work. And as I mentioned, for the compactability issue. So 4.75, 12.5 control mix, it cannot make even the 1½ inch of thickness. So 2 inch was the maximum thickness they can, or the minimum thickness they can make. So we had the 2 inch thickness of the surface layer. But if we place the 2 inch of the wearing surface, we didn't have the leveling surface here. But if we have the 1 inch wearing surface, we place the 1 inch of leveling binder. So, but total is 2 inch. So leveling binder is kinds of cheap materials. So if we reduce the wearing surface thickness, the the cost will be cheaper than other section. We did 4 field testing for friction, noise, and rutting. And then we did the texture profiling using laser at the speed of the 45 miles per hour. And then after construction and every 4 months after construction. And we did the noise test using the microphone close to the tire to detect the sound intensity factor between the tire and the pavement surface. And also we did the friction test using the locked wheel, the friction test device using 2 different tire, red tire and smooth tire. And also we did the measurement in the field under the traffic control using dipstick. Mean texture depth. Mean texture depth of the SMA mixture decreased more than dense grade mixture over time. So right after the construction, the 4.75 SMA and usually SMA mixture provide the higher mean texture depth than other dense grade mixture. But the texture depth decreased more than the dense grade mixture over time. Yeah, but there is some recommendation for this mean texture depth. If the mean texture depth is less than 0.4 millimeter, we have the higher risk of the wet crashes. So all of our section kinds of was above the 0.4 millimeter of the mean texture depth. Friction number, as you can see here, we had a relatively higher friction number in the sprinkle mix right after construction because of the choco chip on the cookie. So, but after several months, it's dropped to, it's dropped because of the section we saw some pop out of the sprinkler chips. So, or some materials on the surface will be rearranged under the traffic. So this might be one of the reason. So SMA mixture generally provide a higher friction number. Sound intensity level. If surface is too smooth or too rough, this cause the higher noise level. If we have the proper texture or the surface void, if we have the noise, this is reflected in the void and then diminish it. But if it's too smooth, this noise is going to the air on the other area. So if the surface is too rough, it creates some noise between the tire and pavement. So as you can see here, is largely dependent on the aggregate size. So 4.75 SMA mixture provide very low sound intensity level, while the 12.5 SMA mixture provide the highest sound intensity level. So usually the 3 decibel difference makes double sound intensity level. So rod depth. Actually, for this rod depth for the 1 year is still very too short to observe the significant rod depth in the field. So we will see the more data. So this is the last section. We have the performance data for 5 from the 5 different testing. But to find which one is the most cost-effective materials, we did the engineering benefit analysis. This is the cost information from the plant. So this column is mixture cost, and this is the next one is construction cost. And then we combine these two, and then we get the total cost, which is the agent's cost. You can see control SMA provide the highest mix cost because it used the PG76-22 highly modified binder. And also 4.75 SMA mixture. To have the small aggregate size, we screen the aggregate from the stop file to have the 4.75 SMA. This additional process cost a lot actually. So that's why we have the very high the mix cost here. And also 4.75 the SMA contains 7.3% of the asphalt binder. And also for the sprinkler mix, we should have the spreader, so it increased the construction cost too. So this is material cost But for each section with different materials and different thickness, we calculate the material cost here. But this column is the bidding price before they do the construction. But after they finish the construction, we get another price, which they really spend the money on this aggregate or the asphalt binder. To do the cost analysis, we should have the usual cost. To calculate the usual cost, this is the cost per hour for driver and the user, the road user. So from the consumer price index. So we have this number, but to convert this number to the 2011 year, so we use the escalation factor. So, and also we have all the traffic data for each section. Using this, all the information, we calculate the total cost. The red one is the usual cost, and the blue one is agent's cost, include material cost, construction cost. You can see the usual cost was 3.62 on this section and this section because there was no leveling binder. So when we have the leveling binder, we had the two lifter. So we blocked the section 2 times. So it increased the usual cost. This is deterministic cost analysis. We just fix all the numbers and then calculate the total cost. But this second one, the blue one, is a probabilistic cost analysis. We allow all the variation of the material cost and then user cost too. So as you can see, 12.5 SMA section provide the highest total cost. Now we have the cost and then performance. But to quantify of the performance for each test, we use the Fisher's LSD statistical method. By using this method, we can rank the mixture for each performance, A to E or something like that. So we put all the raw data in this is the software, and then get the rank A to E or B, C. A and B here, there is a significant difference on the performance. So A, the quart size for the rotating quart size mixture significantly performed better than sprinkle mix. But if we have the A-B, that means there's no significant difference between A and B, but their performance was in between A and B. So we did the same things for the field testing result. And then after then, we assigned some specific number or the score for each group A. For example, for A, we assigned the 10, and then E, we assigned 2. And then convert all the A to E letter to score. And then we sum all of this score using this one, because we have the lab test result and the field test result. For rotating, we did the lab test and field test too. So we combined, but we have the weight factor for each, which is the performance result we gonna give more than the weight. If people trust more on the field testing result, we're gonna give the more impact factor. And also we have so many different the performance. So for example, in the Arizona and Texas, they will give the more impact factor or the weight factor on the rotating performance than fracture. But in this cold area, we will give the more impact on the fracture test result than the rotating. But here, we are still working on this part. But here, I assume give all the one number for each one. So I convert we get all the scores for each performance and then sum, or take the average of this one. And then this is overall performance score. And then this is cost for each section. And then dividing this cost by the overall performance score, we can get the unit cost for each section. So usually the control mixture provide the higher unit cost for one performance score, while this new mixture provide the less cost for the one unit performance. So sprinkle mix with the 1 inch thickness of the wearing surface provide the kinds of, this is the most cost effective section. Yeah, new mixture provide the alternatives using innovative approach to improve pavement performance with the less expensive locally available materials. And also using the fine dense grade, the aggregate gradation, we could get the good density on the thinner layer. And the use of the recycled materials would give more benefit on cost. For control mixture, they use the recycled red materials inside. But in our new mixture, we didn't use any of the recycled materials, the red materials. We still use the steel slag, but we didn't use the red. But if you use the red materials in our new mixture, we can save the more money. Yeah, so that's it. Thank you. Any question and comments? Okay.
If those fibers were chosen by you or someone else for the mix, it seemed like they weren't that effective.
Oh, I did.
Yeah, but who recommended the fibers? It didn't seem to give what the performance they were supposed to.
Actually, at the beginning, we had more than 20 tentative mixture, but we did some literature review. We noticed there are some states or the school, they try to use the fiber or something like that. So we put this mixture in our table to determine. So actually, the fiber mixture and the steel slag mixture is two different mixture. But in the TRP meeting, we combined these two because when we use the fiber, the cost will be increased. But to use the steel slag, we can down the cost, the reduced cost. So that's why we combine steel slag and then fiber.
So I was surprised you said steel slag is cheaper.
At the beginning, actually, we thought the steel slag is cheaper, but now steel production is not that active in Illinois, so the price of the steel slag is going up. Okay. Yeah. But at the beginning, actually, we thought if you use the steel slag, we can reduce the cost. But now, I think it's not. Yeah. But the steel slag actually is a very durable aggregate, though. Yeah.
Any other questions?
Yeah. Also, looking at the cost of production, quartzite was the only imported material, but in the production cost, it was one of the lower for production, lower cost materials.
Okay.
Just not that much quartzite used in the mix, or?
Actually, we use just the 20% of the quartzite in this mixture.
I thought it would be quite a bit more expensive with hauling costs and
yes.
whatnot getting in here.
Why did you choose an impact test for your durability? Use the LA abrasion test. That seems to be like an impact type test. Weren't you trying to measure abrasion resistance or skin resistance or something?
I think in the asphalt materials, I I think we didn't actually, we decided this title at the beginning. So to measure the durability of the asphalt materials, there's no, the standard. So we find Texas DOT used this test for durability. So that's why we use this one. But it's not a common test, actually. Yeah. Yep.
What are your thoughts on the recycling and reuse of these various mixtures? Some of them are standard to what we're using now, so we have an idea. But for some of the more exotic mixes, which ones do you think would be more recyclable or better for the recycling stream? And which ones would you have to be more careful with or could be problematic for reuse?
I think all of this one can be used for the recycling, actually. But since we have the fiber, for the select fiber mixture, since we have the fiber, we don't know how we can recycle these materials, or it's hard to, if we put the select fiber mixture, or combine this mixture with the other, the regular mixture, it's hard to control the quality of the recycled materials. But let me think about that. Is this your question?
Yeah, I'm just thinking, let's say that you get 7 or 10 years out of these surfaces, but you want to get in a process of a sustainable approach to reusing these. Maybe taking the quartzite mix for an example. So these are pretty thin, so they're probably variable thickness layers. So when you go to remill them, you may have a mix of that particular layer plus the layer below might get into the recycling stream. So, would these end up being completely separated stockpiles in the future? Would you just have yet another recycling stockpile for quartzite, so that if you go to make another quartzite mix, and then how critical is the gradation? Because after you mill the material, it's probably a different gradation than what you would use for a virgin quartzite material. So would that be a problem with limiting its amount of usage?
I think about that. I think all of our mixtures work for the recycling after 7 or 10 years, but I don't think that we have some critical issue for the recycling.
I'm sure they can be used somewhere. I'm just wondering if they could be used for such a high quality mix in the future, or if they would have to be used for something else, maybe. Yet to be determined.
I don't think, there will be the issue to use these materials as a recycled materials.
I'm sure we can find a way.
Yeah.
Okay, thank you, SongSu.
I think you're not able to. Actually, that slide in which you have given the scores for TSR and IDT.
Score, this one?
No, the scores which you have given for report. Yeah, this one. How you have given the scores for TSR? Because for quartzite it is about 7 and for 4.75 it is 5.1. But if you see the TSR data sheet which you had shown earlier, so in that the TSR value for quartzite was lesser than for SMA. For SMA it was about 100.3 and for quartzite it was 91.2. So what are the criteria for giving all these?
How do you assign the 7 or 10?
Oh, if you have the A4, it's the maximum is 10 and the lowest is 0.
Yeah, but how did you get the 10? Is that based on its ranking in the
Yeah, ranking and the score. If this mixture has the A for this performance actually. Yes, I show you here. Some mixture has A, B, something like that. So for A, we assign the 10 point.
Does A mean it's the best?
Best.
Okay.
Yeah. So if this durability, we only use the Canterbury loss test for durability. If this mixture has the A rank for the Canterbury loss test, it will have the 10.
But she's talking about the TSR.
TSR. We also did this LSD Fisher's LSD analysis. So if this mixture has the A for that, from that analysis, we'll have the 10. Yeah.
TSR rank doesn't count from the actual strength, it comes from the ratio between the strengths between dry and wet.
High TSR value what is implied this? For SMA, the value is much higher than that for both sides. But the equal handling for SMA is
No,
much
it's the actual strength value or the ratio between them.
And anyways, actually for moisture sensitivity test, that ratio is means it does give a very strong idea about the strength because it's actually a ratio.
Oh, I got you. Right. If you want to go back to the TSR
I think
page.
it's my mistake. I assigned. Oh yeah. I assigned the lower value for the highest one, I think. Because 4.75 SMA provide 100% of the TSR. Yeah.
It was more than 100.
Yeah, more than 100, 1 point something like that. So I think that. Thank you for.
So that sheet in which you are given all the TSR values and moisture.
Back to work.
Yeah.
For segment, you have a value of 91.2 and the dry value is 150.
Yeah.
Off the record.